All right, so in our video, our next video in this series, we are going to be looking at partial sums and talking about how they're going to tell us about convergence of the series. We're going to be trying to look at, can I actually find the sum of this series? And so we need to know if that's a possibility or if it ends up adding up to infinity. So we really can't add an infinite number of terms in the same way that we would add a finite number of terms, because you never get to the end of it. So instead, we're going to look at what the partial sums are doing and seeing if we can figure out a pattern of what we call the partial sums. So if you add up, let's say, the first k of these, like, can you figure out what that sum is? But then maybe you figure out like the k plus 1 sum, and then maybe you figure out the k plus 2 sum and see if those go to a number. So let's look at like a real world example. Suppose that we know that oil is seeping into a lake such that 1,000 gallons enters the first week, the next week it's 500, the next week it's 250, so on and so forth. This continues forever. How much oil is going to end up being in the lake? And you might think like, well, if we keep adding oil, then it's going to be like infinitely big, but we keep adding half of whatever there was before. So if we think of this in like thousands of gallons, just to keep our units down, you can see that like, okay, the first week there's 1,000. The second week there's 1,000 in there, but then we added a half. And then the third week there's 1,000, but we added another half of the half, so we added a fourth, and so on and so forth. And again, you might be like, well, this is going to keep going on forever and ever and ever and ever and ever. But if you look at this partial sum, like, and we try to figure out a pattern of this partial sum, then we see like 1 plus half plus fourth every single time, where this ends up being, if you write this as 1 over 2 to the 0, right? This is 2 to the 1. This is 2 squared. This is 2 cubed. So the first term, I need to take 2 to the n minus 1. The second term, I need to take 2 to the n minus 1, n minus 1. So that's where this comes from. Here, anytime you have 1 over the number, it is okay to then bring that fraction outside. And so I'm saying that this partial sum is equal to this pattern, which I can write as this series right here. Okay, what happens as k goes to infinity? Well, as k goes to infinity, I'm going to end up adding to all of these here. So let's look at that sequence of numbers overall, because if I can figure out what that sequence is doing, then I can find the sum. Okay, so we're going to again list this out, but instead of just the numbers to figure out the pattern, let's actually find the sums. So here's the first sum, here's the second sum, here's the third sum, here's the fourth sum. Now I'm noticing like I have 1.5. I'm getting a little bit closer to 2. 7/4 is a little bit smaller than 2. I'm getting something a little bit smaller than 2. I'm getting something a little bit smaller than 2, but like still getting really stinking close to 2. So it seems that I have a bounding above an upper bound of 2. And so it seems like the sequence of those partial sums is going to 2. If you use some technology in order to find this, you actually see like, if I got 20 terms, okay, so that's the partial sum for 20 terms, I get really stinking close to 2, okay? So it seems like if you keep adding oil to this lake that it's going to go on forever, but really the maximum approaches 2,000 gallons. We'll have a way to find this a little bit later, because this is a geometric a geometric series, and so we'll be able to find that actual sum, but you can use the limit of the partial sums to find S. Okay, so the limit of the partial sums finds your S, and that's actually going to end up being the sum of your series as well. Okay, here's that formal definition of what we just talked about. If you have an infinite series and you look at the partial sums, then the sequence of those partial sums, if you look at those and they converge, then that number is the sum of the overall series. So let's look at a few examples here for us to try to figure out what the sums of these are. So on this first one, I'm going to write out this series. So if I plug in 1, I get 1/2. If I plug in the next one, I get 1/2 plus, so like this is S1, this is S2. I get 1/2 plus 2/3. Here I get 1/2 plus 2/3 plus 3/4. And I'm going to keep going on and on forever and ever and ever. Now, it does kind of follow a pattern where, and you might not see this off the top of your head, but I'm going to show you here. Here I have 1/2. Well, 2/3 is bigger than 1/2. So I'm taking 1/2 and I'm adding something that's bigger than 1/2. Right? So let's see. I know this is bigger than 1/2, so this must be greater than 1/2 plus 1/2. And then same thing, like 3/4 and 2/3 is bigger, so this must be greater than 1/2 plus 1/2 plus 1/2. And so I know that like this is going to keep getting bigger and bigger and bigger. Like I'm adding 1/2 every single time. And not only am I adding 1/2, I'm adding something bigger than 1/2. So this is going to end up being divergent. Okay. All right, let's look at B. So here is S1 would be -1. S2 would be -1 plus 1. Okay, which gives us 0. And then S3 is -1 plus 1 plus -1, which equals -1. So these sums are just going to bounce back and forth. Okay, they're not going to end up converging to anything. And so I'm going to say again that this one diverges. All right, let's look at C. C is going to be a lot like A, where we're going to need to be a little bit tricky with our partial sums here. But let's just look at a few. So S1 is 1, S2 is 1 plus 1/2, S3 is 1 plus 1/2 plus 1/3, and so on and so forth. If you notice here, let's maybe look at S4. One-third and 1/4 is bigger than 1 plus 1/2 plus 1/4 plus 1/4, which I know you're like, where did that come from? But just kind of hang with it here, okay? And so that's bigger. This is equal to 1 plus 1/2 plus 1/2, which is 2. And so I'm going from 1, and then by the time I get to S4, I have something bigger than 2. And if I continue this pattern, you can go all the way down to S8, and you figure out that S8 is bigger than something that's 3. And you keep going and keep going and keep going. And so there's another way we'll look at the divergence of this as well, but 1 over n is going to diverge, okay? Now let's look at what happens when I have the alternating series, however. When I have the alternating series piece, S1 is -1 over 1. S2 is -1 and then plus 1/2. S3 is then -1 plus 1/2 minus 1/3. S4 is -1 plus 1/2 minus 1/3 plus 1/4. And so every time I add a little bit, I then take a little bit away. And so I'm interested to know if these approach a number. So this is, I'm going to do a different color here. So this is -1. This is -1/2. If we have -1/2 and we add 1/3 to it, we get, it's not going to be in fraction form. Let's say, okay, let's do it in fraction form. So 3/6 plus 2/6, so -1/6. And then if I add 1/4, I end up getting that this is -1/6 plus 1/4. 12ths, -2/12 plus 3/12, so -1/12. And so it looks like here that the limit as n goes to infinity of my SNs equals 0, right? And so that's actually going to be the sum. This converges. And so because there's that alternating piece, this is going to end up being a convergent series versus this one is not. Now these two actually have special names, okay? This is called the harmonic series. Let me write it out. This is called the harmonic series, and this is called the alternating harmonic series. Okay, and it's always true that this one diverges and the alternating piece makes this one converge with a sum of 0.